Okay, today, so we're going to be done here. We've got 20 minutes. We got to go harden the paint for 20 minutes, and then we'll. Okay, so we're going to talk today primarily just about the derivative as a rate of change, right? And that's really what it is. We're pretty used to thinking about the derivative as a slope, and we look at it in pretty dry, abstract mathematical terms. But it means, like when we're talking about changing quantities, it actually means stuff that's very applicable to the world. So how would we interpret these? Well, dy dx, that's a derivative. Really what that means is the rate of change of the variable y with respect to the variable x. If we did something like f prime of x, if we want to think of that as a rate, that's the rate of change of f of x with respect to the independent variable x. Okay, y prime, that's another way of saying derivative. That implies the rate of change of y with respect to whatever the independent variable is. So usually that would be an x. And then sometimes we can be more explicit about application. Like if v represents volume as a function of radius, right? And that's how we would look at that function. We'd say r is the input, v is the output. So we would say that as volume as a function of radius. Makes sense. You input a radius, the formula outputs a volume. So v prime of r would be the rate of change of volume with respect to radius. Okay? Think what that's saying. As the radius changes, how fast is the volume changing at a given radius? Okay, it's a little bit strange. We'll talk more about this so you can kind of really get a good conceptual grasp of what we're talking about. If S, like in kinematics, S represents position a lot of times, right? And the input variable for kinematics is a t. So S prime of t is the rate of change of position with respect to time, which we just define as velocity in kinematics. If we did something like capital T of M represents average water temperature as a function of month, that's a function. So T prime of M is the rate of change of temperature with respect to the month, right? So you might find that the tap water is changing temperature the fastest, maybe like probably like about now, right? The weather's getting colder, and so the tap water is going in your sink is going to turn from being relatively warm to pretty cold by the time you get into February or something, right? So these are all functions that we could describe. We could use derivatives to help understand by describing rates of change. Okay, so let's take an example here. Here's a function r of v, and let's define this. It can be used to determine the heart rate r of a person whose heart pumps 5,400 milliliters of blood per minute, and v milliliters of blood per beat. Okay, so this would be something that if you were like a cardiologist would be looking at functions like this maybe to help determine if a person's got a healthy heart. So find the rate of change of heart rate with respect to v, the output per beat. Okay, well, that's what v is. Remember, v is the milliliters of blood per beat, right? So that's output per beat. People that are really fit can pump more blood per beat. Okay, we would just differentiate this using the power rule, right? What's our input or independent variable here in this function? V. What's the output? R, right? Okay. So then how would we want to rewrite this so we could differentiate it with the power rule? Yeah. And now we apply the power rule. We dump that -1 out front. We get negative 5,400 v to the -2, which just becomes that, doesn't it? Right. So there's our derivative. Okay. So then how are we going to interpret this? Let's do a couple things. Find the heart rate at v equals 60 milliliters per beat. Is that an R or an R prime issue? I'll let you think about that for a second. Why don't you guys just think about it, maybe discuss it a little bit internally here. What do you think? Part B, am I looking at R of V or R prime of V? Just R, yeah, isn't it? right? Because isn't that the definition of R? R is heart rate as a function of, really we call that stroke volume, milliliters per beat, of blood per beat, okay? So that lowercase v is stroke volume. Heart rate as a function of stroke volume. So if for a stroke volume of 60 milliliters per beat, we would just plug that into our function and get an answer. So that would be what, 90? That would be the heart rate. Okay, and that would be the point on our graph. That would be the point, like, where would that be? What were we at? So something like right about there-ish. Okay, make sense? Okay. What about C? Find the rate of change. Gives it away, doesn't it? The rate of change at a stroke volume of 60 milliliters per beat. Okay, what's that mean? So what is R prime again? How would I say R prime? R is just heart rate as a function of stroke volume. What's R prime? Good, you always start with rate of change. Good, rate of change of, okay, so the rate of change of heart rate with respect to stroke volume. Okay, what's that mean? That means, what does that mean? What does that mean? If I were to try to find the value of the derivative at 60, at a stroke volume of 60, what's that going to look like? What's going to tell me the value of the derivative or the rate of change on this graph of R? What does derivative correspond to? These are kind of tricky questions until you really start to get a flavor for it. What have we always done with derivative so far? What does derivative tell us? Slope, exactly. It tells us the slope of the curve for a given input value. What's our input value in part C? 60, right? Stroke volume of 60. So at 60, we're really just trying to find the slope of the tangent to the curve there. Does that make sense? Okay, what's that telling us? That's telling us how rapidly is heart rate changing as stroke volume changes for a stroke volume of 60. Okay, and the answer is, well, we could plug in 60 and see. We get 5,400 over 60 squared, 3,600. So what is that? About 1.5? Yeah, so negative 1.5. Right, there's our answer. Negative. Oh, it is. There it is, right there. Whoops. Negative 1.5 beats per minute per milliliter. What's that mean? That's so weird. What does that mean? Beats per minute per milliliter. Any ideas? It's going to change. Like if I put in, if we go to 10, say for some reason we were at a stroke volume of 10. Well, at a stroke volume of 10, I couldn't even do that. I mean, that would be too small. Look what that would give us for a heart rate. If I put 10 in, that would give us 540. That's probably not so good if you've got 5, right? I mean, that's not going to work well. What if we pick 27 for V? If we pick 27 for V, that's giving us a heart rate of 200, okay? If our stroke volume is only 27, as the stroke volume changes, what that tells us is that the heart rate is going to change very rapidly because the slope is steep there. Any small incremental change in stroke volume when V is 27 is a really big change in heart rate. As we get down here closer to something like if we had a really big stroke volume, Like, let's say we had a stroke volume of, let's see here. Stroke volume of 170, right? Then that would mean 170 goes into 5,430 times. That would mean that your heart rate would only be 30 beats per minute, right? That's pretty low. That's why fit people, you guys are aware of that, right? Somebody that really exercises a lot, does their resting heart rate tend to go up or down? You guys know about this? Oh, it goes down, right? If people really are in good cardiovascular shape, their heart rate goes down substantially. Like my dad was he was one of the top 25 marathoners in the world at one point. He was a really, really good athlete. He was the AAU U.S. amateur athlete, distance athlete of the year in the U.S. one year. I mean, really good. I mean, ran sub 223 marathons, was in phenomenal shape. His resting heart rate was, I think at one point it got down to like about 40. I mean, it was really low. About 75 or something, Yeah. So he just had such big stroke volume because he was such a good distance runner that, his pulse rate went way down, right? So if you already are in very good shape, if your stroke volume is big, so you're up there on the curve somewhere, any incremental changes in stroke volume aren't going to make that much of a difference anymore. You're already in pretty good shape, right? But if you're in poor shape and you increase your stroke volume slightly by exercising, that's going to have a pretty major impact on your heart rate. Okay, you see how do we interpret that a little bit there? Okay, it's a weird concept. It's not like we're actually changing it to a specific value. We're just saying that any changes that you make at this point of tangency are going to propel a change in heart rate based on that steep slope. So it's going to be a pretty big bang for your buck. Down here, where the tangent line is less steep, any changes in stroke volume are going to have a more minimal impact because the tangent line is not as steep. That tells us a lot of useful information, right? Okay, let's look at another example. Oh, mine's not like it's that great. I don't know, I'm 60 or something. It's not like I'm not in that great of shape. So, well, I mean, just because I'm doing hill sprints doesn't mean I'm in really good shape. It's dedication is not the same thing as fitness necessarily. So let's not. Yeah, I got a ways to go. So
that's crazy. It was cold outside.
Yeah, it's all right. A little cold's not bad. We'll talk. Hey, that'll be another topic about. We'll talk about how healthy it is to subject yourself to cold environments. That'll be a different topic. That's not today's topic. Put that one in reserve. Okay. All right. So
I'm gonna make a note.
yeah. There you go. Okay, so how about this one here? We got based on this is actually a really important one. This you guys need to know about. Here's my dad hat again. You guys got to know about this. So based on data from a research group, the model for total stopping distance of a moving car in terms of its speed is this. There's the function that models that. Stopping distance S is a function of speed V, okay, velocity V, where S is measured in feet and speed V is measured in miles per hour. Okay, how do we build this? Why does it come up that way? Well, we could actually kind of dissect this. The linear term in the stopping distance has to do with reaction time. So it takes you a certain amount of time to react and push on the brake. And so the car travels a certain distance in that time. And then here's this V squared part. And we'll get into this more in the future when we understand calculus a little better. This will make a lot more sense. This has to do with the extra distance because of our initially high speed, right? What do we find here? So if we take the derivative, what do we get, first of all? Let's calculate the derivative. So there's S. What's ds dt? Or S prime of t. Or S prime of v, sorry, not t. What is that? We can that's just a polynomial. We can differentiate that. That's no big deal. 1.4, right? First term we get 1.4 plus, yeah, 2 times 0.054, so 0.108. I agree with that. V. Okay. So at 55 miles per hour, what is S prime of V? We just got somebody plug that in on you got to pull up Desmos on your phone or your calculator or something. All right. 7.34. Okay. 7.34. What would the units be? What would the units be? Now let's go back for just a second to that last one and compare what we did there. The units of the derivative is the rate of change of heart rate with respect to outputs per beat, right? So it's going to be units of heart rate over units of stroke volume. So that would have been beats per minute per milliliters, right? Make sense? And where do we have that? Beats per minute per milliliter, right there. Okay, make sense? So what's this going to be then? In this case, where we're talking about rate of change of stopping distance per, right, relative to speed, what are the units going to be? Yeah, right. So it's going to be units of stopping distance divided by units of speed. Okay, we'll look at a graph of this in a second, right? Because we're talking about the rate of change of stopping distance. That's the numerator of our rate always, right? With respect to means divided by speed. So we're going to have feet per miles per hour. Okay, that's a weird unit, but it means something. We'll talk more about that. If I plug in 75, I would just get what for my answer? I would get 9.5. Okay, why is that stuff important? What's that telling us? What's that telling us about what's happening at 55 versus 75? Kind of. That's true. I mean, but that's what the function tells us. Like if I just plug, we've got S of V up here. What if I just calculate S, and this is actually really important to know about. S of 55, if I plug 55 into that, what do I get? Ashton, you got your calculator there. What's 1.4 times 55 plus 0.54 times 55 squared?
55 squared?
Mm-hmm.
Okay, I plugged it in right. It's 317.35.
That sounds right. 317-ish. Okay, so that's going to be 317 feet. What is your stopping distance at 75 miles per hour?
Almost there. 408.
We'll just round up, call it 409. Okay, so then let's look at these differences here. So from speed equals 55 to speed equals 75, speed increases by what percent? Well, 75 over 55, that's going to be about, what's 75 over 55 real quick? 1 point.
1.3636.
Okay, so by about 36%. We increased our speed by 36%. What happened to our stopping distance? Stopping distance increases by, so what's 409 divided by 317?
1.290.
Something's wrong here. 1.2, 75.
We're supposed to divide 55 by 75?
You're supposed to divide, yeah, 75 by 55. That's 1.3. I guess that's right. Yeah, so what's 409 divided by 317?
1.2.
What? Is that right?
409 divided by 317? Or 317 divided by 409?
No, 409 divided by 317. Is that really 1.2? Oh, never mind. That's because, no, that's right. What the heck? Stopping distance. This is really goofy. Something's not right here. What? Something's wrong here. Something's wrong. Let's see. Oh, here. This thing got, I've been pulled about 1 million copies of this. So if we plug in, there's that point. Let's pick 75. Oh, I see what I needed to do. Yeah. Okay, I did something dumb there. Yeah, okay, I didn't think that was right. So the speeds increase, if we did that, if we calculated the speeds correctly, that should be 1.7. Okay, so I didn't think that was right. That can't be right. 0.7. What's S of 55? We must have calculated S of 55 wrong. Yeah, S of, okay, we did. S of 55 is 240. There we go. Okay, I knew something was wrong there. What did I say? It was 240? Okay, so then that's about a 70% increase. Okay, look at that. You increase your speed by 36% and you increase your stopping distance by 70%. That's a problem because people are not good at judging that, especially your generation. If you're young, you haven't driven as much, it's really difficult to kind of make those calculations without having driven for years and years and years. People aren't really well adapted to really high speeds like that. When we move around, what do our brains have evolved to be able to move around at slow speeds? You know, we can only run and move at slow speeds. And so we don't ever see these discrepancies that you get when you have really large speeds and frictional effects like that. Person would never have to deal with that, moving around, you know, ambulating around on your own. But when you're in a car, it's different. When you're in a car and you get these really high speeds, you know, these superhuman speeds, our mind tends to think about things in terms of a linear relationship. Our natural judgment would be that if my speed increases by 36%, so would my stopping distance. That's the way our brain works. That is not what happens, though. So what's the obvious danger of this? I mean, people don't stop, right? They don't anticipate things soon enough, and you may not be able to because reaction time is finite. And so you start driving fast, stopping distance increases, accidents occur, right? So what's I put my dad hat firmly on here. What am I telling you? As drive slow, exactly. Don't drive fast. Driving fast is cars are like weapons. Also, kinetic energy, which is the dangerous part of a crash, increases as the square of speed. So you double your speed, you quadruple your kinetic energy. In an accident, you got to dissipate all that energy. That's not good for your body to dissipate that energy when you're in the car. So don't drive fast. You heard it here from Mr. Oya. Okay, the derivative gives us a little bit of additional information about this. What does this mean? The value of the derivative at 55 miles per hour is 7.34 feet per miles per hour. Whereas the value of the derivative ds/dv at 75 miles per hour is 9.5 feet per miles per hour. So my question to you is, any small incremental change in velocity is going to have a bigger impact on stopping distance at 55 or 75? 75, because the slope is bigger, right? What's that tell you? That tells you there's a more aggressive change in the output for small changes in the input. Isn't that what a slope means? If dy dx is steep, that means y is changing rapidly for any little small change in x, right? Here, s, stopping distance, is changing rapidly for any small tweak in the input variable v, right? So that's what derivatives are telling you. Oh, we got to, okay, all right. I wasn't as efficient with that as I thought I would be, but we'll pick it up Monday. That's fine. I'm sure you guys have got stuff to work on. So